So I had to end the movie because it has to be less than 15 minutes. So let's return to the last example I looked at, the one where I'm asking if minus 3 is a quadratic residue or not. So I'm claiming that what's relevant now is the remainder mod 3. So I'm asking whether or not the prime is 1 mod 3. And the claim made sort of visually by these two drawings next to each other is that if I have something which is 1 mod 3, meaning this is white, then I should also find something white up here, because then that is a square modulo the relevant prime. But you can see there's actually a problem here. If you look in this column here and this column here, this is supposed to have something white, and it doesn't. And the point here is that the matrix is simply a little bit too small. So the number I'm looking at is 37. You could relatively easily see that in order to make sure that you meet all the squares, you have to go to half of that number. Of course, the half of 37, maybe rounded up, is 19, so I would have to go to 19 or 18 or something like that to be sure that I don't miss a square. And actually, even if you just put one extra entry, oops, I have to put it, it's transposed, so I have to put it here. No, sorry. Like so. And there you see I get the entry that I was missing before. So what happens here is that there is a nice correspondence between when a number is a square modulo various primes, when -1 or -3 I should say specifically is a square modulo prime, and whether or not that prime is 1 modulo 3. And of course you can keep on going by looking at various examples and see if you can extract various systems, but probably at this point you want a better tool. So I wrote a little program called is quadratic residue, where essentially I go through the various, so I, instead of having this problem with the um, array that I'm looking at being a fixed size, which then sometimes is too small, then I will be systematic and say, okay, I'm asking if A is a if B is a square mod A, I need to run through the i's going from 0 to half of A and see if the relevant squares hit B modulo A. So this is what this little program does. And then I wrote another program that takes some primes, n of them, and puts them in two piles. One is when B is a square modulo that prime, and the other one is when it's not. And so, I mean, you can, this is a little bit more compressed. And so this is the same example that I showed you before, but I'm free of the problem of having data to be too small. And you can see that the pattern that we talked about earlier still is there. So what's relevant is when -1 is a square, that happens depending on whether or not we have 3 or 1 modulo 4 as the remainder, with 2 as a special case. And for -3, you get a similar system. What's relevant is whether or not you are 1 or 2 modulo 3, with 2 and 3 as special cases. Right, so you can, of course, keep on going. And another interesting example is +5. And you can see +5, if you stare at this a little while, it's particularly easy. That's why I chose it, because 5 is half of 10. Right, so you can see that the last digits that we encounter here, with 2 and 5 perhaps being special cases, is here we have 1s and 9s, and here we have 3s and 7s. So this means that the numbers that we encounter that give quadratic residues, 5 as a quadratic residue, those are the primes that are ±1 modulo 5, and the remaining ones are those that give ±2 modulo 5 with 5 and 2 as special cases. So you can sort of keep on going, and when you do this for for a while, maybe a short while, if you're Gauss, who saw this pattern first, is that there's actually a relation between when -3 is a quadratic residue mod p and when p is a quadratic residue mod 3. Because what we saw was, I mean, when is something a quadratic residue mod 3? We went through those cases. That's when it's 1 or 0 modulo 3. Right? And those are exactly these numbers here. Those are the ones that are 1 or 0 modulo 3. We should deal with 2 as a special case because it doesn't fit the pattern in general. And these are the ones that are 2 modulo 3. And when you do the same with 5, you'll see that what's relevant is, again, whether or not p is a square mod 5. So there's something strange going on here, that here it's -3 squareness has something to do with the squareness of p mod 3, and here it's +5 squareness that has something to do with the squareness of the prime mod 5. So you can sort of, after having looked at this for a while, you get the idea that perhaps we shouldn't compare arbitrary numbers to arbitrary numbers. We should compare primes to primes. And this is what this next matrix does here. So I'm just taking all the primes. I'm starting at m plus 1. So this means that I've now given up at looking at the first prime. The first entry I have here is a 1, 1 entry. So the first entries I will have here are the second prime twice. So that's 3 and 3. And so I'm asking if some sort of pattern in, whether or not prime number m is a square modulo prime number n, and I'm putting this in a matrix. Now, because my program returns true or false, it's not so easy to see what's going on here, so I make a little program that just replaces any true with a 1 and every false with a 0, and then I substitute that in, and then now I can make a drawing. So what I have here is the comparison of the squareness of the prime p to the prime q. But I also, and I call this matrix plus, I also want to compare the squareness of prime p to minus p, minus q. So that's the one I call minus, and it looks like this. And I can try to plot them next to each other. This gets a little bit small. I think perhaps I can pull this a little bit, but this is when Maple doesn't like to. Yeah, I'm not sure that makes it any better, but it's sort of tricky to look at all this data at the same time. Nevertheless, there seems to be a relatively straightforward pattern. Right? Some of these lines look as though they are repeated. If you look at the first line here, where I'm comparing, I'm asking, when is p minus p as a square modulo q to when is plus p a square modulo q. So when I'm looking at this, you see some of these rows are repeated. For instance, the first one seems to be the same, and others seem to be inverted. So there's something going on which seems to be systematic, but it's a little bit hard to see. So let's try to use some colors. So what I'm doing here is, now I've taken the plus matrix that compares P directly to Q, and I plotted this in red, and I've taken the minus matrix and I've plotted this in blue, and then also I put the diagonal in as in black. But of course these entries, they overlap. So we don't see the identity matrix in black. It's sort of hidden underneath all these red values here. And also, in the case that there's something which is simultaneously red and blue, the order in which I put these things in will matter. This is ordered in a list, so this Maple sort of knows to put things in the order that I asked to. And the way it's set up is that the last thing will be printed first. So first we printed the identity matrix, which gave us little uh, black boxes here. Then we printed the -1 in blue, and then finally the +1 in red. And so what happens, you can see there's sort of a very clear pattern here. Some of the rows, I only see red. Maybe that's because the red is shadowing some blue, but there are some white zones as well. And in other rows, I see reds and blues and no whites. Right? So there's a pattern seeing when you look in the various rows, there's a pattern that has to do with either you see only red, well, either you see red and white, or you see red and blue. And I can do things where I put things in different orders. So it's the same plot, but I interchange the order of the minus and the plus plot. So that means that the blue will go on top of the red. And we see the same pattern that either there's only white and blue, and so that means that actually all the blue and the white red boxes are in the exact same positions, or we fill up everything um, and you have a situation which is then the same in these two drawings here, which must mean that whenever there's something blue, it's not red, and vice versa. Right? So there's a pattern emerging from this, and actually, if you start looking at what rows are of one kind and what rows are of the other kind, especially with the examples we already looked at, then it's pretty clear that what's relevant here is whether or not the primes are 1 or 3 modulo 4. This is one of the reasons why I disregarded um, the, the case of the prime 2. Now you can actually do this even further and make a plot where I've now used 4 colors. And what I'm doing is I'm showing you, again here the order will matter in various ways, but I'm showing you first I plotted the identity matrix. Now that's gone, it's been overwritten by something further down the road. Then I did the minus plot, but I did not transpose it. Right? So I interchanged the roles of the two primes. And I did this in brown. Then I did in green, I took then I took the -1 in, oh, yeah, maybe those were unfortunate color choices, but let me stick with it. So I took the minus with a transpose and made it green. Then I took the plus uh, with a transpose and made it red. And then finally I took a plus with no transpose and made it blue. And so what you see here is something which is probably not as clear from the other setting, is that there's also some sort of symmetry going on in this diagonal, which of course comes from the fact that I'm transposing things. But you can see that not only is there symmetry in the green and blue and green and red and blue, but of course the overlapping that takes place destroys a bit of that. But there's also very nice symmetry when it comes to the white zones. So actually you can sort of, now let me plot the values that are 1 modulo 4. And you can see that there's a very clear pattern here. Whenever I have something which is 1 modulo 4, that's when I get a white column here. This is exactly the zones where I have 1s.